Okay, and so I'll talk fast. I have less than 15 minutes, and this can be found in the chapter on hypothesis testing and statistical significance. But just to recap, if you go to 121 or just the main points after that chapter, just in case you have a different version, this is in chapter 11, but this is on page 121. And basically, excuse me, that hypothesis testing is basically making a decision about whether or not there's a relationship between your two variables and taking in consideration the sampling error. If it's too much, then you're not able to reject the null hypothesis that's saying there's no relationship or that there's so much error that you can't attribute it to a relationship or you can't say that it's significant. Okay, so the null hypothesis is basically saying the opposite of what you're hypothesizing or predicting. If you're saying there is a relationship, it's saying it's not. And if you're saying that uh, it's in a certain direction, it's saying it's in the opposite direction. So if you say more men are, men will have more or higher income than women, your results will come back as women having more income than men, then that is for the null. The null is actually saying that, the opposite of what you wanted. So hopefully that's not too confusing. So we'll just go on. Take a look at it for yourselves. And then there may be a diagram. For some, it may be helpful. On page 120, you'll see some distributions, and it'll show you the area if your data, if your results fall in that area in terms of the p-value. It will tell you when you can and cannot reject the null hypothesis. So, but when you see the p is 0.05 or less, then that means you can reject the null, which means if it's p 0.05 or less, like p 0.000, you have support for your hypothesis if it is in the direction of what you predicted. Okay, so I think that simplifies things. All right. Okay, and so now I'll just go right into bivariate statistics. It should say just bivariate analysis. Again, keep in mind that the level of measurement and the number of variables will determine which analysis that you'll use or procedure that you'll use to look at the relationship or describe the relationship between your variables. And of course, you can have many more variables, but for the purpose of this semester, we're just looking at only two. All right. So the first analysis that we'll look at is the crosstab, and you use the crosstab if your independent variable was any combination of or if it was nominal or ordinal. Okay, and if your dependent variable was nominal or ordinal. All right, so what I wanted to say was it can be any combination. You can have an independent variable that's nominal, dependent, nominal, independent, ordinal, dependent, nominal, independent, nominal, dependent, ordinal, independent, ordinal, and dependent, ordinal. Okay, all right, confusing, but I think you have the idea. Any combination of nominal and ordinal would fit with the crosstab. And then the p-value that we'll look for when you run the crosstab, if you're looking at the output, they'll have a number of them, but we're looking at something, and don't get it confused with anything that has to do with Pearson's R, but it's called the Pearson's chi-square p-value. So you're just looking for that particular p to find out if your results are statistically significant and if you can reject the null hypothesis that says there's no relationship between the two variables. So nominal, ordinal variables, if you have two of them, any combination of nominal and ordinal, you would use the crosstab. And you would first of all have to have your results in the direction of what you predicted. For instance, if you say, we'll stick with that example, more men will have, we'll just say that, we'll say men will have more satisfaction on their jobs than women. So if you pose that hypothesis, then you would have to look for results, uh, like a table, a crosstab when it comes back, and it's just a chart with the heading for your variable men, women, and then satisfaction, yes or no, or if it's an ordinal, none, some, a lot, or something like that. But you would look at, just to simplify it, if we had the satisfaction yes or no, we would need to have the high number in the cell that corresponds with the column men, and yes, that number would have to be higher than the cell that corresponds or intersects with the column women and yes. All right, so that would explain or uh, result in men being more satisfied. It would explain that men are more satisfied than women in their job. I hope that makes sense without a visual. So we'll just go here and now look at the graphical display. Just like with the procedures, uh, this will be determined by the level of measurement and the number of variables that you use. But to simplify it, if you have the crosstab, what corresponds with that is the clustered bar chart. And clustered meaning that we're now dealing with two variables, and different than univariate where we just looked at bar chart, we now have something called the clustered where we can look at gender, one variable, the independent variable, that is nominal or ordinal, but this is nominal in this case. And then we can look at another, how it affects another variable, and this is ordinal. A little bunched up here, but none, little, a fair amount, some, a little bit, and so forth. A very great deal. At the high end, it should be. And this is satisfaction with family life. So someone hypothesized that there was a difference between these two. Maybe more men or more women had, maybe more females had a higher level of family life. And there's a number of ways you can crunch these and combine them together. But if you look at the very end, which is the highest level of very great deal, it looks like if you hypothesize that women or females were more satisfied in family life, and these are the categories or the levels. Only looking at the green, this represents women. They have a lot more than men. So they have, if you hypothesize that, then step one, you have support for your hypothesis so far with step one that is in the direction of what you predicted, because there are more women who had greater satisfaction, okay, with their family life. All right, and the next step would be to look at your p-value for your output, the results, and see if you have support by looking at the p and seeing if it's equal to 0.05 or less. 0.000 would be wonderful. Okay, and that just means that there was no error, sampling error associated with the results. All right, and we went through this, and I'll probably pull up a couple of other slides as well. We'll see. So means differences means comparison of the mean. Basically, your independent variable is nominal and your dependent variable is interval. So this is just basic. And you can run this as an actual procedure, an analysis that you can run. But then if you want to test your hypothesis, then you would use something like, if you wanted to hypothesize test is what I wanted to say, you would use a t-test or the ANOVA based on the number of categories for your independent variable. So if your independent variable has two categories, uh, and it's nominal, so dichotomous, independent variable, two categories, two levels, like gender, male and female. And then we're looking at an interval level dependent variable like income or age, then we would use something called the t-test. If we have more than two categories, something like if another researcher wanted to, again, use gender, but they wanted to include transgender here, then now we have three categories. If we had four, that would be fine too. We would still use something called the ANOVA, or the analysis of variance. Okay, as long as we have the independent variable nominal with three or more categories, like for instance, race, African American, Caucasian, Latino, and Asian, and other. Those are five categories, but that would be fine to use with the ANOVA as long as the dependent variable is interval level. What goes along with this, if you have two categories, you can use the box plot. If you have three, box plot. Some folks what can I say about the box plot? Some folks do not appreciate it, but you can also use something called the dot plot, or any other type of graph where you can distinguish between the height of one category in comparison to another, and see which one has the higher mean. Okay, look in your text for that. Another analysis is the Pearson's R, or the Pearson's product moment correlation, but Pearson's R is how we say, and this is a test of two interval level variables. So remember, there's a difference between nominal and interval and interval. All right, this is interval. Again, just counting numbers, regular numbers. And the results of this will range from -1 to +1. We're not talking in terms of connotation, but how strong it is determines in absolute terms how high that number is. All right, so the closer you get an R 0.9, 0.99, an R equals 1, that's a very strong relationship between, or correlation between the variables. So if you're predicting that height is correlated to weight, the taller someone is related to how much they weigh, and the results show that the R is 0.9, and that's a very strong relationship. All right, the magnitude of the relationship. The direction just means it's positive. As the numbers in your independent variable go up, like 4 feet, 5 feet, 6 feet, as that independent variable, those levels go up, weight will go up, like 155, 160, 165. That's a positive direction. If both of your fingers are pointing up as you count, then for your independent variable and your dependent variable, the direction of the, as they increase, then that's positive. As you go down, that's also positive. So the shorter one is, the less they weigh. All right, so it's the same thing. The taller you are, the more you weigh. The shorter you are, the less you weigh. But now if you hypothesize that the taller you are, the less you weigh, then that would be indicative of a negative relationship. Same thing, the shorter you are, the more you weigh. Again, that's a negative relationship. So we're not talking of whether it's in connotation negative or positive. We just mean the direction. Okay? 0, no relationship. If R equals 0, there's no relationship. The scatter plot corresponds with that as well.